In Chapter 10, we'll be studying circles, and although Section 10.1 is titled Properties of Tangents, a lot of this section is just going to be terminology about circles in general. So to start, let's define what a circle is. A circle is a set of all points in a plane that are equidistant from a given point called the center of the circle. So looking at the diagram, here is the center, and the circle is defined as the set of all points that are equidistant to that center. So from here to here is equidistant from here to here. So we just keep stringing those equidistant points along, forming this circular picture. You name a circle by its center. So if we're looking at the diagram on the right, if we called that point for the center A, we would call the circle, circle A. And now for even more terminology. A chord is a segment whose endpoints are on a circle. So referring to the diagram at the right again, this green line is considered a chord since it's a segment and the segment's endpoints are located on the circle itself. A diameter is a chord that contains the center of the circle. Now this should be different than what you usually think of as the diameter because we are now thinking of it as a chord. So it's a chord that contains the center. So we're looking at this blue line. It's still a chord since it's a segment whose endpoints are on the outside of the circle, and notice that it also goes through the center. So again, this is different than what you normally think of as the diameter, but this is the way you should be thinking of it in this chapter. Now, one more thing that is not specifically defined in this chapter is the radius. So looking at this diagram, it's the red segment right here, and a radius is technically defined as a segment whose endpoints are the center of the circle and a point on the outside of the circle. It is half the length of a diameter. Now on to two more terms. A secant is a line that intersects a circle in 2 points. So now we're looking at this diagram down here. The green line is the secant. So notice that part of a secant line is a chord since from here to here would be a chord. So a chord is a segment, a secant is a line, and part of a secant line would be a chord. Something that you definitely need to write down in your notes is that a chord is a segment and a secant is a line. And one more time, a chord is a part of the secant line. Then the last one is a tangent is a line in the plane of a circle that intersects the circle in exactly 1 point. So a tangent line just intersects the circle in 1 point, while a secant line intersects the circle in 2 points. So again, secant and tangent lines are both lines, but a chord is always just a segment. The place where a tangent line intersects the circle is called the point of tangency. So anytime you hear that, you need to make sure you realize that that's just the place where the tangent line is intersecting the circle. It's where the tangent line and the circle have a point in common. Now let's apply all that terminology to example number 1. Tell whether the line or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. Notice they are naming the circle C since the center of the circle is point C. So let's get into this. Part A says segment DC. Since it's a segment, I know it cannot be a secant or a tangent since those are lines. So we are minimizing our number of options here because it's a segment. So if you look at DC here, you go from the center of the circle to the outside of the circle, which is just a radius. Part B, segment BD. So again, this is a segment, not a line, so it can only be a radius, a chord, or a diameter since secants and tangents are both lines. So we have BD, so from here to here, although it's part of this line, it would be a chord since it's a segment. Notice it's a segment symbol. It's a segment whose endpoints are on the outside of the circle. So segment BD is a chord. And again, for part C, we have segment DE, so it cannot be a secant or a tangent since those are lines. So DE is a chord who goes through the center of the circle, so that would be a diameter. And finally, part D, line AE. So this time we are finally talking about a line, so we're only considering options secant and tangent as our answers. And looking at the diagram, line AE is intersecting the circle in exactly one point, which would be point E. So this would be a tangent line. And I know this doesn't ask, but if you were asked for the point of tangency, it would be point E, since it is the point that both the line and the circle share. And now on to some more terminology. This has to do with talking about radii and diameters. So if it says a radius and a diameter, they mean the segments themselves. And if it says the radius and the diameter, they mean the lengths of the segments. So a radius or a diameter means the segments themselves. If it says the radius or the diameter, they're talking about the lengths of the segments. Moving on to example number 2, use a diagram to find the given lengths. So part A says the radius of circle B. So circle B is the bigger circle. So the radius goes from the center out. So that would be 1, 2, 3 units long. Part B, diameter of circle A. Circle A is the smaller circle, and diameter is a chord that goes through the center of the circle. So here would be a diameter, so it is 1, 2, 3, 4 units long. Part C, the radius of circle A. I don't even need to look at the diagram for this. The radius is half of the length of the diameter. So if the diameter is 4, then the radius is 2. And then for part D, it says the diameter of circle B. So again, I don't even need to look at the diagram, since I know the radius of circle B is 3. The diameter is twice that, so the diameter would be 6. Another thing that is discussed in this section is the intersection of circles, or in some cases how the circles don't intersect at all. The first way that they can intersect is where they have 2 points of intersection. So they have 2 points in common, like in this first diagram. So notice that they have 2 points, the red dots intersecting. A second way that they can intersect is so they have 1 point of intersection. These are also called tangent circles. Think back to the definition of tangent lines. It's a line that intersects the circle in one spot. So 2 circles that intersect in 1 point would be called tangent circles. So sometimes the circle can be inside of another circle and they're intersecting in one spot, or they can be sitting next to each other and sharing 1 point. And finally, the 2 circles could not intersect at all, so they have no points of intersection. So they could just be sitting next to each other but not sharing any points, or one circle can be inside the other circle and they share the same center. In that case, they are called concentric circles. So again, when one circle is inside of the other circle and they share the same center, they are not intersecting at all, and they are called concentric circles. One other thing that is discussed in this section is something called common tangents. Let's define that first. So a common tangent is a line, ray, or segment that is tangent, so it intersects it in one spot, to 2 coplanar circles. So you can see in the diagram 2 different scenarios, one where the tangent line is kind of sitting in between the 2, and another scenario where the tangent line is on top of the 2 circles. But again, a tangent only intersects the circle in one spot, so that is the same for common tangents. And in example number 3, we're going to be exploring more about these common tangents. So it says, tell how many common tangents the circles have and draw them. So part A, we have 2 circles that are intersecting in 2 different spots, and how many common tangents can they have? The first scenario is where we can have a common tangent on this side going through both circles in one spot, and same scenario on the other side going this way. So in this case, there's only 2 common tangents, because if I kind of draw any other lines, it'll be intersecting the circles in more than one spot. And remember, tangent lines can only intersect in one spot. And problem B, kind of the same situation. I could have tangent lines this way coming down and this way, but I could also have them kind of going this way diagonally through the circles. So there's actually 4 common tangents on this problem. And in part C, we have the same situation where we can have them coming along the sides. So we have at least 2, but also I could have one going through the middle because that line would intersect both circles in exactly one spot. So there's actually 3 common tangents for part C. For part D, there's only 1. If I draw this line right here, it would be intersecting the circles in one spot at the same time. However, if I draw any other kind of lines, they would be intersecting the circles in more than one spot and therefore not be tangent. So again, just 1 common tangent. And finally, for part E, we don't have any common tangents because if I were to try to draw any kind of line that's intersecting the outer circle in one spot, it would not intersect the inner circle. And if I was trying to draw a tangent line on the inner circle, it would hit the inner circle once but hit the outer circle twice. So there are 0 common tangents for part E. And just to use some more terminology from the last slide, part D would be called tangent circles since they're intersecting each other in one spot. And in part E, these would be called concentric circles because they are not intersecting and they share the same center. And now we have 2 theorems. Our first theorem is theorem 10.1. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So notice it uses the phrase if and only if. So we can use this forwards and backwards. So to begin, a line is tangent to a circle. So if I know that this line is tangent to the circle at point P, then I know that it is perpendicular to the radius. But if we read it backwards, if we know that a line is perpendicular to the radius, then we can assume that that line is a tangent line. And theorem 10.2 says tangent segments from a common external point are congruent. So this is kind of vague, so let's break it down. It says tangent segments, so we have 2 segments that are tangent to the circle here at R and at T, and they have a common external, so on the outside point, so that's point S. As long as that happens, we can assume that RS is congruent to TS. So now let's put these theorems to use. Here's example number 4. In the diagram, segment AB is a radius of circle A. Is segment BC tangent to circle A? So if segment BC was tangent to the circle, then it would be perpendicular to the radius. So if it was perpendicular, we would be forming a right triangle, which means we could use the Pythagorean theorem to see if 25 squared plus 60 squared is in fact equal to 67 squared. So let's do that. 25 squared plus 60 squared is 4,225, and 67 squared is 4,489. So since these are not equal, that means this is not a right triangle. So therefore, according to theorem 10.1, BC is not tangent to circle A, because if it was tangent, it would be perpendicular to the radius. Let's look at one more example where we are going to put that theorem 10.1 to use. So here's example number 5. In the diagram, S is a point of tangency. Find the radius R of circle T. So in this problem, we are told that this line is tangent to the circle. So we can automatically assume that it is perpendicular to the radius. So now notice that a right triangle is formed. So that means we can use the Pythagorean theorem. So the 2 legs would be R, so R squared, plus the other leg, 48 squared, which would be equal to the hypotenuse squared. But in this case, we actually have 2 lengths for the hypotenuse, R, and then this part, which is 36. So the total would be R plus 36, and then we square it. The biggest misconception that kids do is they think when you take a binomial like this and square it, that you could just square the R and square the 36. But R plus 36 squared means R plus 36 times R plus 36. So we actually have to distribute it all out. So R times R is R squared. R times 36 is 36R. 36 times R is 36R. And 36 times 36 is 1,296. So after combining like terms, I would get R squared plus 72R plus 1,296. So when I write out my problem now, I would have R squared plus 2,004 is equal to, I'm just going to transfer this part right here. So R squared plus 72R plus 1,296. Now it's just a matter of solving for R. Notice that there are R squareds on both sides of the equal sign. So if I subtract r squared from the right side and from the left side, both of them will cancel each other out, leaving me with 2304 equals 72r plus 1296. So now our problem becomes super simple. I'm just going to subtract that 1296 over, and we end up with 1008 equals 72r. Divide both sides by 72, and you end up with r is equal to 14. But remember, r is the radius, and we were given a unit in this problem, so it'd be 14 centimeters for the radius. And our last example puts theorem 10.2 to use. So here's example number 6. In circle C, segment DA is tangent at A, and segment DB is tangent at B. Find X. So again, theorem 10.2 says that if we have two tangent segments that share a common external point like we do here, then those two segments are congruent. So we can assume that BD is equal to AD. So I can just take what they're equal to and set them equal to each other. So 6x minus 8 equals 25. I would add the 8 to both sides. So I would get 6x equals 33. Then just divide both sides by 6. And it's okay that we don't get a whole number. 33 divided by 6 is 5.5. So x equals 5.5. That's it for this section. Make sure you jot down anything you didn't understand that we can go over in class, and we'll see you then.